AP Chemisters, this is Mrs. Vanderlei bringing you 17.9 Blankwalle. This is the last section of thermodynamics, and again, it goes back to the idea of equilibrium. Section 17.8, we introduced the idea of Q. And if you recall, when we talked about Q back in equilibrium chapters, chapter 15, that the Q is your initial set of conditions to see where you are as for equilibrium. Are you going to shift to the right and make more products? Are you going to shift to the left and make more reactants? So we're going to tie this in now to equilibrium. We had said earlier back in chapter 15 that if Q equals K, you're at equilibrium. Okay, so if your initial set of conditions was equal to the equilibrium constant, you are at equilibrium. So how does this tie in then to thermodynamics, to delta G? So this is a thermodynamic view. Equilibrium occurs at the lowest value of free energy available to the system. Well, let's see what that is. So do you remember this curve from chapter 17.8? Go back a few pages, you'll see this. So here is, we're going down, all right, that's where delta G is negative, so it's spontaneous, like going down the hill, all right. Over here, we're going to go down the hill here, going the opposite direction though, and that's where delta G is positive. Look what happens, you're at the very, very bottom of this hill, all right? What does it say right here? Q equals K, and you are at equilibrium. So what does that mean? You're at the lowest possible part of this curve. So here with the pressures, we have the optimal pressures for equilibrium to occur. So you have the same, in this case, amount of gas evaporating as you have the, the liquid evaporating as you have the gas condensing. That's what's going on right here. So let's go back to section 17.9. So the equilibrium point occurs at the lowest value of free energy available to the reaction system. So delta G, not delta G naught, delta G equals 0 and Q equals K. So what's going to happen here? Let me scroll down. So it says at equilibrium, delta G at the present conditions, the non-standard conditions, equals 0 and Q equals K. So for delta G naught. So here we go. That's the equation from section 17.8. where the delta G at the non-standard conditions equals delta G naught at standard conditions, the stuff that you looked up in the chart, plus RT ln of Q. So let's see what happens next. We have, let's see, I'm going to plug in those values. So delta G equals 0, I did that, and Q equals K, I did that. So now solve for delta G. So I'm going to subtract RT ln of K from both sides, and I got delta G equals negative RT ln of K. And so a couple things that's kind of important here. Let's kind of use this. I'm going to put them over here. All right, and how does this help us? When K is a small number, what happens when K is a small number? What is the natural log of K when K is less than 1? So if you punch on your calculator, what is the natural log of 0.2? All right, it's a negative number, isn't it? So what's a negative times a negative? It is positive. So when K is less than 1, natural log of K is negative, therefore delta G is positive. Well, what did we say here? If delta G is positive, we learned earlier that it is not spontaneous, is it? We also said if K is less than 1, what does it favor? It favors the reactants. So what does this mean? It is not spontaneous in the forward direction. However, it is spontaneous in the reverse. You are going to have more reactants. That's what this says, okay? How about when K is greater than 1? Well, what's the natural log of a big number? It's positive, isn't it? So it's a positive times a negative. It is negative. So ln of K is positive, delta G naught is negative. What did we say there? Delta G is negative. Oh, it's spontaneous in the forward reaction. What did we say when K is greater than 1? We said that you're going to favor the products. You're going to make more products. That's what's going on here. All right, and then finally over here, what if K equals 1? Well, what's the natural log of 1? It's 0. So this whole term is 0. And this reaction happens to be at equilibrium under standard conditions. So you're right at that cusp of, does the reaction go or not? So can you maybe influence by temperature? And as you know, yes, you can, because delta G naught equals delta H minus T delta S. So if we manipulate the temperature, we can make it spontaneous. But wait a minute, I thought if K equals 1, then it's going to be 0. Oh yeah, K is dependent on temperature. So if you manipulate the temperature, you're going to also change the K, and you can make it go positive then, all right, or make it go negative, whichever way it goes, whichever temperature you choose, okay? So that's what's going on in these down here. So if K is less than 1, that means it's going to favor the reverse. All right, so the reverse reaction is spontaneous, okay? What if K is greater than 1? We're going to favor the products, and look down here. Here's my reaction going the forward. And if K happens to equal 1, you know, that doesn't happen all that often, but it can. All right, you're not going to really favor either one. All right, you're not going to favor the products or the reactants, okay? Let's go to the next page. All right, here's problem number 16. Use a tabulated free energies information to calculate the equilibrium constant for this reaction. Well, if you have your book handy, you can go to the very back of the appendix of your book, and you find the chart with delta H, delta G, and delta S on that. Or I also gave you a copy of those back when we did chapter 17 after chapter 6. I'm not sure if you can find those, but you might want to look those up, all right? So if this is all I give you, calculate K, all right? What is the K for this reaction, okay? Well, if you recall from chapter 17 the first time around, we said that delta G is equal to the summation of the products minus summation of the reactants. If you look up on your chart, what is NO2? Well, the delta G for NO2 is 51.3. Maybe you want to write that down if you haven't found that yet. So here, let's do that. So then if you look up the dinitrogen tetroxide there, what is its delta G value? So if you can look it up, that's great. I looked it up, so I got 97.5. So this is looking up off of the chart, okay? So then how am I going to figure out what delta G naught is? So why don't you go ahead and calculate yourself. All right, this is what I did. Maybe that's what you did too. And, oh, come on. What are you doing? There you go. And then I got delta G equals a positive number. What did we say earlier if delta G is a positive number? Is it spontaneous at this temperature? The answer is not if it's a positive. All right, now we need to calculate K. Before you actually do the math, what do you think K is going to be, a big number or a little number? Think about that. So here's the equation we just learned, and let's plug in some numbers, okay? By the way, what is R? Oh yeah, 8.314 what? Is it kilojoules? It's joules. So here's my 5.1 kilojoules per mole, negative, here's my R, here's my T, L, and a K. So at this point, what can I do? Well, the K's cancel out, don't they? But what doesn't cancel out are the joules. The joules don't cancel out. So what do I need to do? Oops, what am I going to do next? I converted my kilojoules into joules. All right, so I multiply that by 1,000. Now what can happen? Well, we can once again cancel out the kelvins. I guess I didn't do that yet. What else can I cancel out? I can cancel out the joules. That's Joules, by the way. And I can also cancel out the moles. So now I'm left with no units. And is that a problem? And the answer is no, it's not, because a natural log has no units, all right? So go ahead and do the math. What do you get? All right, I got negative 2.1. And now how do I solve for K? It's e to the negative 2.1. And what do I get? Hopefully you're doing this. I got K equals 0.122. Hopefully you did too. Or probably K equals 0.12 if I have 2 sig figs from right here. So this is always what you need to be considering. What does this mean? What does it mean? Well, delta G is positive. Knew that. K is less than 1. Knew that. That is very consistent. So the reaction is what? Not spontaneous in the forward direction. So what does that mean? It favors the reactants. So you're going to have more N2O4 than you do NO2. All right. So let's look at problem number 17. It says calculate the delta G at this reaction. So we're going to do the opposite. I gave you Kp, you give me delta G. So before we start, let's think about this. Kp is a big number. Look at that, 81.9. What do you think that means about delta G naught? What do you expect to happen? I bet it's going to be negative. Why don't you go ahead and do this totally on your own? And so stop the video, and when you are done, come back. All right, so I put this equation up. Why would I put this equation up? Because that's the equation that relates delta G naught and K. There you go. So, excuse me, now I'm going to plug in some numbers here. So remember, R is 8.314, not 0.0822 or 21, I mean, because I need joules, Joules. And here's my temperature and natural log of 81.9, all right? So what I did next, I multiplied these two numbers together. I found the natural log of 81.9. And so what does that mean? I'm going to scroll up here. So when I did all that work, I get delta G is negative 10,912. So delta G is negative 10.9 kilojoules per mole. So what does this mean? Hey, we were right, doesn't it? Delta G is negative. Yes. K is much greater than 1. Yes. What does that mean? The reaction is spontaneous in the forward reaction. So what does that mean? I'm going to make a whole lot of iodine monochloride. All right. Yes, I will. So I know you don't have a whole lot of space. You might want to write small in problem number 18. All right. I end up using a lot of space on this one. And I apologize. I should probably reformat your paper here. So anyway, go ahead and work through this problem. This is about as the most complicated kind of question that you can be given. I give you the delta H of formations. I give you the delta S of formations. You need to calculate the K. All right, so pause this. It's going to take you a little bit and come back. All right, welcome back. Hopefully you got it. So I first found the delta H of the reaction. So it is the sum of my products minus the sum of my reactants. So I have 2 times negative 826 minus 0. Notice these are both zeros. 4 times 0, 3 times 0. So I get negative 1652 kilojoules, right? Well, let's try the delta S. Remember, 2 times your product minus this whole quantity are my reactants. And there you go. And so when I do the math for delta S, I get this, then I get this, and my final answer is this. So remember my goal. I'm trying to find delta G. Why do I need delta G? Because I'm trying to find K, all right? So now I'm going to use these values I just calculated. And do you see a problem here? Hey, let's check out my units. My kelvins cancel, but what's the matter here? This is a joule, J-O-U-L-E-S. And this is a kilojoule. So what do I need to do now? I need to probably get one unit into another, all right? So I converted into kilojoules, and so I have delta G naught is equal to negative 1490 kilojoules. So if you did not get this number, I would stop this again and now use this to solve for K again, all right? So if you need to, go back and resolve for K if you did not get this number. My guess is that you may have forgotten to convert into the same units, okay? So go ahead and pause this if needed. All right, so now I'm ready to rock and roll, and let's solve for natural log of K. So I have the value I just calculated here equals negative RT ln of K. Notice that my K's canceled out, but what's now wrong? Oh man, I have to convert back into joules or kilojoules. So I decided to try a little bit different route. I converted this into kilojoules. I could have converted this into joules if I wanted to. I decided, well, what the heck, try something new and different. Let's convert that into kilojoules. So then now what happens, I can cancel out my K's, right? And I have kilojoules and kilojoules on both sides. So I can take this. I'll multiply these two first together. And that's what I did here. All right. Oh, look what else I did. I got rid of the 2 negative values, didn't I? So I got rid of my negatives. I multiplied these 2 together. So then I got natural log is 600.8. So what does that mean now? Wow. E to the 608 is one heck of a number. Oh, here it is huge. huge, all right? Huge to the 260th power. What the heck? All right, so what does this mean? Well, if you looked at the delta G value, let's scroll up, here it is, negative 1490. That's a huge negative number, isn't it? Kilojoules even, that's huge. Look at K, it is huge. What does this mean? The reaction is really spontaneous. That's crazy, isn't it? All right, so it all hopefully makes some sense. Let's go to the next page. All right, so the reaction A is in equilibrium with B, has an equilibrium constant less than 1. What can you conclude about delta G for the reaction? Think about that again. Delta, or H, not H, what is that? K is less than 1. What happens to delta G? Go ahead and circle your answer. I hope you got C. That's the right answer. If you remember the equation, delta G equals negative RT ln K, the signs are going to be opposite. So if K is less than 1, G is greater than 0. Okay. Well, let's check out this next part, and that's going to be the rest of this section, isn't it? All right, so if we know that delta G naught is equal to negative RT ln K, but delta G naught also is equal to delta H naught minus T delta S naught. So I want to know what the dependence of K is on temperature. Remember how I alluded to earlier that if you were to manipulate the temperature, you can make that last reaction, 2 pages ago, become spontaneous. But what else did I warn you about? If you mess with the temperature, you're going to mess with the K. And therefore, you can make that delta G naught equal a negative number because the K is going to change, all right? So how is this going to happen? Well, I'm going to zero in on this part of the equality. Remember, if A equals B and A equals C, then B equals C, right? So it's a transitive. So let's go ahead and just solve for natural log of K. So what am I going to do to both sides? I need to divide both sides by negative RT. And I want to revamp this, all right, because this isn't a great looking equation. I have T over here and T down here, but no T over here. Maybe I did have coffee instead, I don't know. So let me rework this, all right. Let me take each part. So this is equal to, I split it up, negative delta H naught over RT. There we go. All right, plus, notice how the two negatives cancel out? And then I canceled out the T, so delta S over R. So what does this tell me? Now I can look at this. So there is a relationship between K and R and T. Now, looking at this by itself doesn't really help me a whole lot. It would be a whole lot easier if I could graph this. I'm a visual person, you know that. So if I can graph this, and maybe then I could really see what's going on here, okay? So let's go ahead and put this in terms of y equals mx plus b. So I'm really kind of close here. This could be my y. This whole term is mx, and this is b, but I want to know what the t is, right? That's going to be my variable. What happens if t changes? So I'm going to kind of like take that term t in the denominator out, all right? And why would I do that? Because now I have my y, my negative h over r is my m, here is my x, and here's my plus b. So again, I'm a really visual person. What is this going to look like in a graph? There you go, all right? So if I could graph the natural log of the K constant times 1 over temperature. Here's my y, here's my x. Well, what is this line right here? That's my slope, isn't it? Notice it's a negative slope. Why? Because it's negative delta h over r. So what is this point right here? Oh, that's the y-intercept. That's the delta s over r value right here. So now I can look at this so that the natural log of K is this kind of a negative relationship to 1 over temperature, right? And from there you can, well, plug in some numbers and see what happens, all right? I bet as t increases, let's reverse this, the natural log will increase, but not in a linear fashion. It has to be 1 over, but it's still going to go up probably in an exponential fashion. And so as temperature goes up, the natural log of K is going to go up. Therefore, K is going to go up, all right? So as temperature goes up, K goes up. And hopefully that makes more sense to you, okay, in most reactions. It's going to really depend on if delta H is positive or negative, isn't it? Uh-huh. All right. I can rewrite this into a 2-point form, by the way, And there it is. So if I gave you like some data with some temperatures, oh, silly Mrs. Vando, I left something out, didn't I? There it is. I put this back, turn back in again. So here is how, if I just gave you some data and I gave you some temperatures and some equilibrium constants, that's how you can solve for something. Okay. So I believe that is the end of chapter 17. As always, don't wait to be great. Bye-bye.